Hello everyone and welcome to another Würth Elektronik webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took your time to participate in our webinar. The topic of today's webinar is Advanced Wireless Power Transfer course. Our speaker today is Christian Merz, who is working as a product manager at Würth Elektronik ISAs. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar. This means that you cannot ask us questions via the microphone. Nevertheless, you have the opportunity to ask us your questions with the chat function. You will find that in the webinar control panel. The webinar will be about 30 minutes long. After that, we have scheduled 10 to 15 minutes for our Q&A session. And if we don't have the time to answer all your questions, we will answer them via email after the webinar. And if you still have any other questions left after the webinar, just email us at webinarteam@we-online.com. At the end of the webinar, you will be also asked to participate in a feedback survey. Of course, we would be pleased if you take the time to fill out the survey and help us to improve our webinars. You will also receive the link to the presentation you will see and also to the recording of this webinar only in the next few days. So now I will hand over to our speaker, Christian, and I wish you a good time with our webinar.
Thanks a lot, Markus. Also from my side, my name is Christian Merz. I'm a product manager at Würth Elektronik. I also do customer projects and also a little bit R&D in the field of wireless power transfer and simultaneous near-field communication. The topic of my webinar today is wireless power transfer advanced training. But first, I want to show you how you can determine different WPT system parameters like coupling factor and the resonant tank capacitors. Then I want to give you some coil-specific considerations and present our wireless power products. At the end, I want to demonstrate our 200-watt development kit. How does wireless power transfer work? So, of course, at first you need a DC power source, which is connected with any kind of oscillator. So for the oscillator, you can use any oscillator which you want. For example, a Pierce oscillator, full bridge inverter, a Rohr converter, or for example, a voltage controlled oscillator. And this oscillator has to be connected with the so-called resonant tank. So the resonant tank consists of a capacitance and in series with the transmitter coil. So closely coupled to the transmitter coil is the receiver coil. So on the receiver side, we also need a resonant capacitor, and the resonant frequency on the secondary side has to be in the same range like at the transmitter side. Then, of course, we need a rectifier at the secondary side, which can be, for example, any DeLore or full bridge or synchronous rectifier or anything else. Then we have our load, which we want to supply. So the magnetic field between the RX and TX coil is concentrated in the volume between the two coils. And the TX and RX coils are inductively coupled. So the distance between secondary and primary side is in the millimeter range, so about 1 to 10 millimeter. Let's have a look at the magnetic resonance system. So as I mentioned before, we have an primary inductance, the secondary inductance, which is connected through the coupling factor. So we are in the kilohertz regime. As I already mentioned, we have short distances. and we can easily calculate the maximum transmission efficiency, which is for high Q only 1 minus 2 over K times Q, which is also called the figure of merit. So for one single coil, we can also calculate the so-called coil quality factor, which is omega times L over R. R is the AC resistance, which also depends on the frequency. Now let's have a simplified look at the coupling factor. Now let's assume we have an inductance with a series resistor, which includes all the ohmic losses of the inductor. So then we have a secondary and primary inductor with the primary resistance and the secondary resistance also including the load resistance. So when we now calculate the impedance of this whole system, we can use Faraday's law of induction and Kirchhoff's law, then we get to a very simple equation. So now if we short the secondary side, then we can get a very simple relation between the short circuit inductance on the primary side and the self-inductance on the primary side, which is 1 minus K squared. So we can easily solve for K, which is this formula. Now we can use this formula, only we have to measure the short circuit inductance and the self-inductance on the primary side. And then we can determine the coupling factor. So how can we do this? How can the coupling factor be determined by measurement? So at first, we have to determine the transfer distance and the transfer frequency. In this example, I used a distance of 3.4 millimeter and a frequency of 100 kilohertz. So as I mentioned before, we have to measure L1 dashed, which is the short circuit inductance. So we have to short the secondary side and measure the inductance of the primary coil. Then we have to measure the inductance of the primary coil when the secondary side is open, which is L1. Then we can simply integrate these two measurement values into our formula, and we can determine the coupling factor for this certain distance. So now we can also calculate very easily the resonant tank capacitors. So as you might know, the formula to calculate the resonance frequency is 1 over 2 pi and the square root of LC. So if we solve this to C1, we get this formula. So L1 we already measured. We just insert it into the formula, and we can easily calculate C1, which is the resonant capacitor at the primary side. Then for the secondary side, we can simply measure L2 dash, which is the secondary inductance and with the primary side opened. Then we just integrate the measurement value and can calculate C2. Now, if the coupling factor and the resonant tank caps have to be determined for different distances, a variable spacer can be used. So you see here the variable spacer, which measures the distance. And on the table, we have the primary coil, and we glued the secondary coil directly to our variable spacer. Then we increased the distance, and for each value, we measured the short circuit inductance and the self-inductance. Then we determined the coupling factor dependence of the distance. So now let's have a look on some coil-specific considerations. So, as I mentioned before, the figure of merit is a very important measure for the efficiency of wireless power transfer systems. So now on this axis, you can see the maximum efficiency, and here you can see the coupling factor. So for different quality factors, as I mentioned before, you can calculate this very simply. So now let's have a look, for example, when we have a theoretical value for the Q of 1000, So independent of the coupling, we have a very, very good theoretical maximum efficiency. So for example, when we have a low Q factor of 25, for example, then we have, for example, for a coupling factor of 0.4, only 80%, compared to almost 100% for Q factor of 1000. So if the Q factor is low, then the coupling factor is very significant. So that means that the high Q coil allow a long transfer distance and higher freedom of positioning. So as I mentioned before, the coil quality factor can be calculated with this formula. So now let's think about the resistance. So this, as I mentioned before, is frequency dependent, and this is influenced by two effects, which is the skin effect and the proximity effect. So the skin effect says, well, for increasing frequency, so the current density is accumulating at the surface of the conductor. So with the penetration depth, delta is related to the frequency and can be calculated with this formula. So to reduce the skin effect, we have to lose Litz wire. The second effect is the so-called proximity effect. So when we have a look at two conductors which are adjacent and we have some current flowing through the conductors, then where a magnetic field is creating at both conductors, and also in both conductors we have some eddy currents. So the result of this eddy currents is that the current density is not homogeneous, but is higher at the edge of the conductors, as you can see here. Here you see the cross section, the current, and it's not homogeneous. So the proximity effect causes current constriction or current displacement in closely spaced conductors. Now let's have a look at the AC loss behavior of wireless power transfer coils. As you can see here, we have the rated current and AC current and the DC rated current. The relation of this is called the D rating. On the x-axis, we have different frequencies. As you can see here, the D rating for Litz wire is not so high compared to the D rating of solid wire. So this is the proof that the Litz wire is better and outperforms the solid wire counterparts. So the solid wire coils with high density of turns show the strongest D rating. For this, for example, this is the 47 microhenry coil, which has a very high density of windings. So the AC behavior of each coil is determined by the interplay of wire type, winding geometry, number of layers, density of turns, etc. So if you're interested in this topic, you can read our publication, which can be downloaded at our homepage. Now let's have a look at the coupling versus different TX and RX coil combinations. On the transmitter side, we use a G coil, which is very often used by our customers, which is A10G design with a Q factor of 180. And at the receiver side, we are looking at different coils. For example, the 207, which is this coil, and the 210, which is this coil, the 309 is this one, and the 213 is this one. So, and let's have a look at the distance of 6 millimeter. And we also calculated the figure of merit. So as you can see here, the figure of merit between these two coils is 118. So with the 110 and the 210, it's only 16% lower. But when we use on the receiver side a coil which is much smaller, for example the 309 or the 213, then the figure of merit decreases to 39% or 31%. So as you can see here, it is very important to have a similar size on the receiver and transmitter side. So now let's have a look when we use on the RX side some transmitter coils which have a similar effective area like the transmitter coil. And as you can see here, we have on the receiver side on the same coil, and these two coils, as you can see here, the derating, so the figure of merit only decreases about 7 or 8%. So because the transmitter and receiver coils have a quite similar area. So that means the inductance, the coil area, Q factor are influencing K and the maximum efficiency. So now let's have a look on the coupling versus air gap. Now we have a transmitter and receiver coil, and we increase the distance on the vertical side and do not change the horizontal distance. So this graph shows the coupling over the distance of the coils over the radius of the coil. So when the distance and the radius of the coil have the same value, then you see, okay, we have a very low coupling of 0.1. The coupling factor drops already below 0.4 at the distance of half of the coil radius. So when you look here, so we have for half of the coil radius, we already have a very low coupling factor of 0.4. So this is valid for any combination of transmitter and receiver coil which are the same and have a circular shape. Now let's have a look when we have a horizontal displacement. So we have a transmitter coil here, for example, and we just shift the receiver coil in the x direction. So then we can see these graphs for different distances compared to the radius of the coil. And here we see the displacement dependent on the radius of the coil. So when you see when the displacement is very low, as 0.1, then we have for example, for 0.1 distance relation, we have 0.9 for, and then it decreases very quickly. Also, for if the distance and the coil radius is the same, then we have a very low value, which is not changing very much. So if you can see here, from I would say 0.3, it decreases very quickly. So this is also very important, the lateral displacement. Now, what products do we have? So we have the broadest portfolio of wireless power coils on the market, which are in total 65 coils. So we have 24 receiver coils, which use a magnet wire and have a size of 6 to 48 millimeters and a power range of 5 to 80 watt. Then we have 28 transmitter coils, which all use Litz wire, and about 50% of them are designed due to the G standard. The size is 20 to 75 millimeter, and the power range is about 40 to 400 watt. Then we have 8 error coils, which are all designed due to the G standard, which are good for if you have any application where you have want to magnetize a very high area, then you can use these error coils. For example, if you have a small receiver and it's sliding on the surface, then for example, this coil supplies your receiver, or this coil or this coil. So it's all defined in the G standard. So, and one of our newest products are the WPT and NFC coils, which where we have 5 different coils, so 2 for the TX side and 3 for the RX side. And at the inside of the product, we have our WPT coil, which is for, this example, A10 G design. And at the edge, we have our NFC antenna. So with this coil, with this article, we can transfer energy and communicate with NFC at the same time. So the sizes are about 40 to 65 millimeter, and we have a power range for the wireless power coils of about 20 to 100 watt, and we use magnet wire for the receiver combi coils and Litz wire for the transmitter combi coils. Now, also do customer-specific coils. So it's often the case that the customer has his own device and he needs a special shape or a special inductance and certain lead lengths or something like this, then that's no problem. You can just go on our WBT website and use our wireless power coil inquiry sheet, and then we will give you feedback if we can do it or not. So please keep in mind that you have a MLQ of about 5,000, but it also depends on the price of the coil. So now let's have a look at the 200 watt development kit. So the 200 watt development kit you can see at the wireless power section. Then just go to the 200 watt kit section, and then as you can see, we won 2 prizes for this development kit. There's a very good solution for wireless power up to 200 watt. There's a current profile which is almost sinusoidal to avoid any harmonics and to be resistant against EMC. Then by changing the switching frequency at the output of the output voltage can be regulated, and you have an automatic and a manual mode. So with manual mode you can change the switching frequency. So when it's near to the resonance frequency, then the output voltage will be increased. So it is scalable from very low power to 10 watt to high power of 10 kilowatt. And the MOSFET switch close to the 0 crossover points, which is called zero voltage switching, to have an efficiency of more than 90%. So I made a test measurement with the 200 watt kit with 200 watt output power, and I reached a DC to DC efficiency of 94%. This is also scalable for many different voltages and currents, and there is also a data transfer implemented from receiver to transmitter. And if you're interested in the functionality, you can just read our app note number 70, where the functionality of the 200 watt kit is described in detail. Now you can see here the transmitter board, the coils which are included in the 200 watt kit, and the receiver board. Now let's have a closer look to these boards. So for the transmitter board, we have input voltage of about 19 to 24 volts and a maximum input current of 10 amps. And on the other side, we have just put in our transmitter coil. So we have here our structures for EMC protection and signal filtering. Then we have here our resonant tank, which is a series resonance circuit for better magnetic coupling between the 2 coils and to have a better efficiency. Then we have here our microcontroller, which gives out the PWM and the encoder and the operating modes and other signals. Here we have the full bridge circuit and bridge control, which converts the DC current to the AC current. And here we have different interfaces, like for display board, for example, is RS232, for debug, and then incremental encoder. Now let's have a look at the receiver side. So we need some smoothing capacitors for stable output voltage. Then we have here our active rectifier, which transforms the AC current to DC current. Here we have our resonant tank, which it's the same one like on the transmitter side, and we also have some interfaces and a microcontroller. So on the interface, you can, for example, you have a I2C interface, for example, for a temperature sensor or anything else. At the output, we have output voltage of about 19 volts and an output current of 10 amps. Now, let's go to the information material reminder. So what materials do we have? So as I mentioned before, we have our own wireless power section where you can read our technical papers. For example, the AC loss behavior of wireless power transfer coils, that I mentioned before, and 3 technical papers about simultaneous wireless power and NFC. We also have a FAQ section where the mostly asked questions are stated, and you can also read the answers to these questions. So we also have our mix and match table where you can have a look on the transmitter and receiver coil, and for example, you want this combination on the transmitter side, the 101, which is a GA1 design, and on the receiver side, for example, you chose the 205, then you can just click on it. Then you get automatically to our Red Expert wireless power resonant tank app. You can see here that chosen transmitter coil, here the receiver coil, and here the calculated coupling factor for this certain distance which we measured with, which is the mentioned 3.4 millimeter distance. And you also get the caps on the secondary side. Here you also have some graphs for the transmitter and receiver, which are the inductances, Q factors, temperature rise depending on the DC current, and the permeability of the ferrite. So we also have a new trilogy of wireless power transfer, which includes basic principles, WPT systems, and applications. So what are our USP, our selling points? So we have the broadest publicity available portfolio of wireless power coils, as I mentioned before, which are in total 65 coils. So we also do customer-specific coils, and we have a high-volume product line. So we can also produce millions of coils per year. It's no problem for us. So we guarantee lifelong availability of all wireless power coils from stock. So all the 65 coils will be available as long as you live. We also support our customers with our local sales, face-to-face, on-call, and expert teams. And we also offer webinars like this, and customer training and supporting tools like Mix and Match and Red Expert. So thanks a lot. If you have any questions, you can ask me now. Thanks for your attention.
Yeah, so thank you, Christian, for your interesting presentation. Yeah, as you have mentioned, now we would like to turn our attention to your questions. And so we wait also a little until some questions come in. We will have a look at them now. Also, just a hint before we start, if we don't have the time now to answer all your questions, we will answer them later on via email. And if you still have any other questions left after the webinar, just email us at the shown email addresses. Okay, but Christian, here I can see the first question. Is it possible to automate the measurement of the coupling factor?
Yes, that's a very good question. So as you can imagine, you have to measure a lot of values if you want to determine the coupling factor for lateral and vertical displacement. So we automated this measurement by using a so-called XYZ table, which automatically change the X, Y, and Z direction, as the name say, and then we can measure the coupling factor for every position.
Okay, thank you very much. Then let's go on with the next question. Which program can be used to simulate the coupling factor as a function of horizontal and vertical alignment errors?
So there are many simulation programs which can do this, but we prefer ANSYS Maxwell, and as the measurements and the simulations fit quite well, which is very good, and we make 2D and 3D simulations depending on the design of the coils.
Okay, thank you very much. Then let's go on. Yeah, customer says, or an attendee says, thank you for the great presentation. Thank you, you're welcome. What is the availability of the 200 watt kit? And what is the, yeah, okay, it's double in, but yeah. So what is the availability?
So it's available right now. You just have to go to your sales, to my sales colleagues and ask for an offer, and you will have it within 2 days. So you can test it, and you also get the schematics, the Altium files, all application notes, all the material you need to start with your own wireless power.
Okay, thank you very much. So then let's go on. What is the maximum efficiency that can be achieved with the 200 watt kit?
Yeah, as I already mentioned in my presentation, so the efficiency is far beyond 90%. So the maximum efficiency I have measured so far was for a very high power of 200 watts at the outside, was about 94%.
Okay, good. Then next question, Christian, how to measure L2 to calculate C2 with a short or open L1?
So the L1 was opened.
Okay, thank you very much. Then I think we still have some time to, yeah, but we need some time to have a look at the next questions. I see there are a lot of questions coming in right now. So yeah, if we can't answer it in the live webinar, we will answer it later on via mail. Okay, Christian, next question. Are there coils for RFID or NFC applications in the portfolio besides the wireless power transfer coils?
Yeah, not in the standard portfolio. As I mentioned, we have our combi coils, which have the WPT coil in the inside and the NFC antenna at the outside. But we also offer customized NFC or RFID coils, so that's absolutely no problem for us.
Okay. The next question, what data rates are possible with the WPT systems?
So the 200 watt kit, we have a so-called in-band communication. So because of the low frequency range of 100 kilohertz to about 200 kilohertz, we have a very low data rate of some 100 bytes per second. To increase the data rate, we make some research on the NFC. So we are just on the way to develop an NFC add-on board, which enables data transfer up to 424 kilobits per second, which can simply be plugged on the top of the 200 watt kit, and then you can start with your simultaneous wireless power transfer and NFC communication.
Perfect. Okay. Yeah, then I think we still have some time for some more questions. Christian, then are there any recommendations you have on an integrated wireless receiver IC to use?
Well, it depends on your application and on your power, and if you need, for example, a Qi certified system. So for Qi, there are many different wireless receiver ICs, and of course, you also need a transmitter IC, which is Qi certified, and you have to fulfill the standard, of course. But if you are not, if you do not need the Qi standard, you can also use any other IC from TI or analog devices, depending on your application. For example, when you want to load a battery, there are some battery charger ICs which are very good, which are, for example, from Linear Technology or Maxim or TI. So I can send a list afterwards per email of some very, very good ICs, where also some simulation models are available.
Okay. Yeah, so thank you very much. Then I think there is one more question we can answer right now. What is the definition of the rated current?
The rated current is the current where the temperature rise at the surface of the coil is increasing up to 40 degrees centigrade compared to the ambient temperature.
Okay. Yeah, so now we are finished with our webinar. That was our last question. So I see there are some questions left, but yeah, as mentioned, we will answer them via email afterwards. So thank you very much from my side for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Christian, for your time today.
You're welcome.
So I hope you will hear us at our next webinar, and I wish you a good day. Thank you and goodbye.